Hey, AP Chem, welcome to Chapter 5. We're going to talk about gases. Fair warning as we start this chapter, it's not a long chapter. It's pretty short, so we'll probably get through this material pretty quickly. Okay, so like most chapters, we're just going to talk through some basic definitions. And then along with the characteristics of gases, along with the gases chapter, we're also going to talk about some basic characteristics of gases. So our first big unit that we just finished recently was on solutions. So we're going to talk about gases during this chapter. Now, gases are similar to solutions. They're both fluids. But there's a couple things that are a little bit different about them. The other thing to know about gases is there's a section on the AP test where they kind of ask you like super random facts just to see like how much do you know about chemistry? How familiar are you with the chemicals that we're talking about? And they tend to hit gases once in a while in those super random facts. So let's talk through just a couple really basic characteristics of gases so that you know just a little bit more about them before we move on. Okay, so first of all, when our like most common gas that we're going to talk about is air, and air is mostly nitrogen. It's about 3/4 nitrogen. So as you're breathing, the majority of what you're breathing is nitrogen. Nitrogen is a very stable compound, extremely stable compound. It's fairly inert. When it does react with something, it's a pretty violent reaction because there's so much energy in that nitrogen bond, stabilizing it, that to rearrange that, you're going to take all that stable energy, and it's now going to be this fairly unstable compound that's going to want to react pretty violently back down to that stable N2 molecule. So most of what we're breathing in is nitrogen, and most of it is fairly stable, super stable nitrogen. The next biggest majority of air, thankfully for life, is oxygen. Oxygen is about just under a quarter. Air is just under a quarter oxygen. And then there's a whole bunch of other gases that make up kind of like the last 2 or 3% of air. If you hear the term vapor, we talked about this a little bit before, but vapor is something that at STP is normally a solid. And then for whatever reason, that solid becomes a gas, and we refer to that as a vapor. So like if we're at STP and we're talking about gaseous water, we would call that vapor, because at STP, water, the majority of water naturally occurs as a liquid. If we're talking about nitrogen, however, we would call it nitrogen gas, because at STP, the majority of nitrogen is going to exist as a gas. So that's what the difference is between that term vapor and gas. Gases expand spontaneously to fit whatever container they're in. And so it makes that volume extremely versatile. You can condense a gas. You can also expand a gas very easily. We can do it inside our little high school lab right here. Not a difficult thing to do. Liquids are also technically compressible, but we can't compress a liquid inside this room. But we definitely can with a gas. Gases are going to form homogeneous mixtures. So that means that the composition of the mixture, no matter what sample you take, is going to be the same. Homo means the same. So a homogeneous mixture means all the composition of the mixture, no matter where you take the sample, is going to be the same. And this occurs no matter what you're mixing. For solutions, this occurred as long as the two things you were mixing were alike. If the two things you were mixing were polar, then your solution that you formed was going to be homogeneous. But if the two things you were mixing were not alike, one was polar, one was nonpolar, that solution you made would not be homogeneous. It'd be heterogeneous. But gases do this no matter what you're mixing. You can mix water vapor, which is polar, and nitrogen gas, which is nonpolar. You can mix those together, and the gas is going to form a very homogeneous mixture, even though the two things aren't alike. And the reason that it does this is one of the things that gives gases almost all of its properties, and that is that the molecules in a gas are really, really, really far apart from each other. They're very far apart from each other. There's the majority of gas is space. If you look at a body of gas, only about 0.1% of that volume is actually taken up with the molecules themselves, the protons, neutrons, and electrons that make up that molecule. So that's not a very big part of the volume of a gas. So the majority, if you blow up a balloon with gas, the majority of what's in that balloon is actually space. And because of this, because the molecules are so far apart, they really don't interact with each other very much at all, especially not under normal standard conditions. And so it doesn't, their interactions with each other don't really determine a whole lot. Not like solutions. If you're looking at a solution in a container, the molecules in that liquid actually take up about 70% of the volume. So about 30% of the volume that you look at is actually going to be space. 70% of it are the molecules themselves. And so those molecules in a liquid are much closer together, and their interactions with each other matter. They make a difference. So that is one of the big driving forces between the characteristic of a gas versus characteristics of solutions, is just that massive amount of space that we find between gas molecules and that lack of interaction of the molecules of a gas compared to, relatively little amount of space in a liquid where the interactions of the molecules really matter and come into place and decide properties. Okay, so as we get into gases here, one of the big things we're going to talk about is pressure. The pressure of gas, pressure on gas, pressure by gas, all of that stuff. And so we talked about pressure already a little, but let's just recap. So pressure will represent pressure by a P. Pressure is going to be a directional force. So pressure is going to be in a specific direction. Atmospheric pressure is going to be, in the direction that gravity pulls. Vapor pressure is going to be on the sides and surface of a container. So pressure is going to be a directional force. When we talk about pressure, sometimes what you'll see is that you'll see something like 760 torr to the left. You can see a direction in that pressure measurement. Now, we in chemistry don't deal with the direction a whole lot, but if you get into physics, if you kind of pursue physics a little bit farther, then you'll start to merge these like direction and measurements together. Now, pressure is made up of two other factors. Pressure is a derived unit. It's derived from force and area. So we talked about this a little bit also, if our force, if you're trying to describe the molecules of the atmosphere, then the force would be gravity pulling on all of these little molecules. That would be the force. And then the pressure is measured over a specific area. And we talked about the ice skater before. if we have a person, let me erase this real fast. Okay, so think about the two different scenarios. Think about a person standing on ice. We'll give this person arms and a ponytail. Okay, versus a person standing on ice. With ice skates on. Oh, those are cute ice skates. Okay, so which person is exerting more pressure on the ice? And so in order to answer this question, we have to think about both of these factors, the force and the area. So think about the person on the top, right? Their force is going to be their body weight being pulled down by gravity. So if it's the same person in both pictures, they're going to exert the exact same force, same body weight, same gravitational pull. The force is going to be the same in both cases. Okay, so now let's look at the area. So the area in the first, so this force is being applied over a specific area. And the area of the first is the sole of the shoe. Okay, so there's like a foot-shaped spot on the ice, and all of the force is being applied in that specific area. In the second one, there is not a foot-shaped spot on the ice. It's a blade. It's only where the blade touches the ice. All the force is being concentrated into that tiny little strip of metal that's sitting on top of the ice there. And so the top one has force over a specific area. The bottom one has force over a much smaller area. And so the bottom figure is going to have a greater pressure because it's the same force over a smaller area, same force over a smaller denominator, right? And if your denominator gets smaller, then your term, pressure, gets larger. And this is why, like we talked about before, as you're ice skating, you're actually instantaneously melting the ice into water. Just that strip of ice where your ice skate blade meets the ice, that actually instantaneously melts into water. You glide over that water you've created. And as soon as the ice skate is gone, that little strip instantaneously freezes again because the pressure has been released. It's kind of a cool concept. Next time you go ice skating, you can think about this. Okay, so if we look at, now that we kind of know what, that was a terrible circle. What pressure is, force over area, let's look at force a little bit more closely. So force, the equation for force is mass times acceleration. So if either one of these components increases, force is going to increase. If mass increases, force increases. If acceleration increases, force increases. And you can think about this in terms of like cars or shopping carts rolling down the road, right? If you have one shopping cart and it's rolling down the sidewalk, okay, and it runs into, let's say, a parked car, because that gives you a nice little visual inside your head. All of you recent drivers, here's a fear all of us carry around inside of us, that a shopping cart is going to smash into the side of our car, right? Okay, so think about one shopping cart hitting the side of your car and how much damage it's going to do. Now think about if someone's like running behind that shopping cart and into your car, right? The shopping cart was accelerating, it was speeding up because someone's starting to sprint behind it. It's going to do more damage to your car. It hit your car with more force, right? Okay, so now let's think about that scenario a little bit differently. Let's say one person is walking with a shopping cart and hits your car. Think about the damage it's going to do. Now think about if it was one of those like massive chains of shopping carts, the ones where, they're collecting all the shopping carts to bring them back into the store. So you have this massive chain of shopping carts. Someone is still just walking very gently, very nicely with all of these shopping carts, and the whole chain hits your car, right? There's going to be more mass there. It's going to do more damage to your car because it's going to hit your car with more force. So force is this product of mass and acceleration together. And this is what we've been talking about too the whole time, right? If you go back to the ice skaters on the side here, we talked about how their force was a gravitational pull. So the mass is contained inside their body, right? It's their body mass. What's the acceleration in that case? So real quick here, we're having a physics day today. So velocity, right? Velocity is distance over time. It's how far something goes over time. We tend to talk about velocity as like speed. They're very similar. Velocity just has that directional component to it. So if velocity is distance over time, how fast something is moving, acceleration is the change in velocity over time. So it's how fast your speed is changing. Are you accelerating? Are you decelerating? So what is the acceleration when we're talking about gravitational pull? It's gravitational force. So gravitational force, 9.8 meters per second squared. That is how fast gravity causes an object to accelerate as it is falling, basically. Okay, so this is acceleration due to gravity. That's our A. And then the mass is kind of your body mass. We tend to say body weight. It's kind of a misnomer, but you get the idea, right? So it's your body mass that's multiplied by this force of gravity, how fast gravity causes something to accelerate. And that's what we get as our force or our body weight. So our body, we're totally on a rabbit hole here, but let's finish this thought. Our body's weight is our mass times acceleration due to gravity. So if you change, that's why if you go to the moon and gravitational acceleration due to gravity changes, you're going to be a different weight, right? Okay, so we have rabbit trailed. Let's just kind of concisely come back to touch on what we're going to deal with in chemistry specifically. So we are going to deal with pressure in chemistry. Pressure is a component of force and acceleration together, force divided by acceleration, and force is a product of mass and acceleration together. And so if we look, we're getting into all of this so that we can look specifically at the units. So let's look at the units of force first. So if force is mass times acceleration, mass is going to be kilograms. This is our scientific measurement of mass. And then acceleration, like we talked about, acceleration is how fast the speed is changing. So it's actually going to be meters per second squared. So meters per second would be speed or velocity. And then we have this additional, like, how much does it change over time? So we get this second S in there. Okay, so force is going to be measured in kilogram meters per second squared, which is called a Newton. So if I ask you how much you weigh, you should not tell me I weigh 70 kilograms. That's not your weight, it's your mass. Your mass is measured in kilograms. Your weight is going to be measured in kilogram meters per second squared. Remember, this factor is the acceleration due to gravity. And so your weight, it actually takes into account how much mass you are multiplied by this acceleration due to gravity. And that is in newtons. So you should tell me that you weigh, I don't know, 630 newtons, which would be an obnoxious way to answer if someone ever asked you how much you weigh, but it is actually technically the correct unit to measure in. Okay, so this brings us to pressure. If force is measured in newtons, see here, force is measured in newtons, and area, right, length times width gives you area, is going to be measured in newtons squared or meters squared. So a Newton over meters squared is going to be a Pascal. PA, it's a Pascal. So the first unit of pressure, or the SI unit of pressure, is a Pascal. And this is where a Pascal comes from. 1 Newton per meter squared is 1 Pascal. So when you're looking at pressure and you're like, these units are so weird, where did these units come from? This is where the units come from. A Pascal comes from a Newton meter squared. Now, Pascals are not super common in industry. Any industry that deals with pressure, it's pretty rare that they're going to deal in Pascals. And so we're going to talk about how a Pascal is related to these other units of measuring pressure that are much more common in industries that deal with pressure. Okay, there we go. So again, Pascals are the derived unit when you're talking about force over area, right? Here we go. 1 Newton meter squared is 1 Pascal. But again, it's not the most common form. And so let's look at how a Pascal is related to these other forms of units for pressure. Now, a bar is a pretty common unit. If you ever find like a little device that's stuck to the wall of homes, my grandparents used to have one, or ships. If you are on a pretty serious sailing ship, you may find kind of a device that they can use to measure the pressure, atmospheric pressure around them right then. That is probably going to be measured in bars. And so here's that relationship between pascals and bars. What is that? 1, 2, 3, 4, 5. So 100,000 pascals is 1 bar. Now, we don't use bars in chemistry a whole lot. You might see them if they're like trying to get you to do a conversion problem or something like that. But bars are not very common in chemistry labs, but they're extremely common in like nautical industries. Millimeters of mercury. This is one you're going to see. Chemists use mercury a lot. And so this is literally measuring the height of mercury in a tube in millimeters. If there's 760 millimeters of mercury in the tube, then they'll take that reading, they'll take that measured height, and that's the reading for the pressure in millimeters of mercury. So Mercury used to be a super common thing to fill tubes with in order to measure pressure or temperature. Mercury, as we all know, is fairly toxic. It also doesn't exit your body. It gets stored in bodies, and over time it can do a lot of damage. And so industries are trying to move away from mercury, and so they tend to fill like thermometers with alcohol now. They're like alcohol-based thermometers. So mercury is a little less common, but it's still a really common unit. So we actually do use mercury, millimeters of mercury in chemistry. And 760 millimeters of mercury is equal to 101.3 kilopascals. Now, you might actually memorize this conversion just because you're going to have to use it a couple times in the book problems, but it's not a measurement you need to know off the top of your head. It's not a conversion that you have to have in your back pocket. And in fact, I'm pretty sure it is on your reference sheet. Might be worth going to check. So millimeters of mercury is a unit that we'll see a lot in chemistry. Torr is another unit. And what a torr is torr is just another name for millimeters of mercury. So you can measure up the column for your millimeters, and you can either communicate that height of that column in millimeters of mercury, or you can communicate it in torrs. They're the same thing. A torr is a millimeter of mercury. So we'll see torr a lot too. Torr is a pretty common unit to see. So millimeters of mercury is pretty common. Torr is pretty common. And then there's one more. So 760 torr is 1 atmosphere. And this is the unit that we've been talking about this whole time for STP. STP, the P for STP is at 1 atmosphere. If you're standing at ocean level on a normal day, it doesn't have any extreme weather going on. Your pressure is probably, the atmospheric pressure is probably fairly close to 1 atmosphere of pressure, also known as 760 torr, or 760 millimeters of mercury. So this conversion, if you happen to memorize any conversions from this page, that would be the one to know. Torr and atmosphere are both very common units of measurement for pressure in chemistry. Again, I'm pretty sure this is on your reference sheet, and if it is not, then don't spend your time memorizing conversion factors for pressure. Spend your time learning the concepts and the other equations that we're about to run into. But now I told you. Welcome to the units of pressure. Now you have seen them all. Now you kind of know, they are really interrelated. They're not independent from each other. One was derived from another one. There are relationships all over the place. If you ever need to convert between one unit of pressure into another, and you're working in a lab, you can always just pull out Google and say, how are pascals and bars related again? And it'll give you this conversion. So you should walk away from the slide saying all of these units of pressure are related to each other, and there's way too many of them. And we should have just figured out one and stuck with it, but we didn't. So now we know that they're all related to each other. Moving forward, we will probably be dealing with either atmospheres, torrs, or millimeters of mercury. Whew. Okay. So that got a lot of our definitions and kind of basic concepts out of the way. So now we're going to go through some basic ways that pressure is measured. We kind of know what pressure is. We have some basic characteristics of gases. We kind of know the units that we're going to measure pressure in. Now, what do the devices look like that we use to measure pressure? Okay, so let me introduce you to the barometer. Oops. Wrong hand. The barometer. Okay, so This was probably the first way that people started to use a device to measure pressure. Okay, so what they did was they took a tube and then they filled that tube with mercury. And then they took that tube and then they flipped it upside down into a bowl of mercury. Okay, so here's a bowl. It has some mercury in it already. And then they took this tube, they filled it all the way to the top with mercury, and then they flipped it over so that the mercury was submerged like that. Okay. And then what happened is this whole column of mercury is really heavy. Mercury tends to be a really dense element. It's also one of your only liquid metals. And it's this whole column of mercury is very heavy. And so the mercury actually falls down. It, instead of being filled to the top, it actually falls down a little bit and it gets maybe to like there. Okay, so the mercury falls down in the tube and it leaves. So where does that mercury go when it falls down in the tube? It comes out. It comes out into this bowl. And so the mercury level in the bowl then rises also. Okay, so here is our newly risen bowl of mercury. And the mercury has fallen down in this tube. And so what is left there in the top? There's space there. What's in that space? And if you said it's a vacuum, you're right. It's a vacuum. And this is one of the reasons they used mercury, is because think about if they had used water. What would happen in that vacuum of space there? Water would come out of solution and would fill that space, right, with water vapor. We talked about that like phenomenon before. Whenever you get this evacuated space, molecules from the liquid are going to escape that liquid phase and go into the gas phase, and they're going to establish a vapor pressure on top. Well, this doesn't happen with mercury because mercury has this extremely strong attractive force for each other. In fact, you know how in a graduated cylinder, you have to read the graduated cylinder at the bottom of the meniscus, right? You read it from the bottom, not the top. And you kind of have to ignore this curve because water is super attracted to the glass. And so because water is super attracted to the glass, it's going to climb up the glass a little bit on the sides, and it's going to leave this dip in the surface of the water that we call a meniscus. Well, mercury actually does the opposite. Mercury is very, very attracted to itself. And so if you were to put mercury in a graduated cylinder, what you would see at the top is actually a curve the other way. So this mercury tends to attract to itself and pull away from the glass sides, and it gives you a curve in the opposite direction. And so when you're reading, the level of mercury, you need to have a container who's kind of calibrated for this so you can read the level of mercury at the opposite end of a meniscus. Okay, so all of this to say, mercury is super, super attracted to itself. And so mercury does not escape from the liquid to establish vapor pressure up top. It doesn't do that. It doesn't really establish a vapor pressure up top, which is ideal for a barometer because we don't want a gas up here that's exerting a pressure pushing down. We don't want that. We only want to take into account atmospheric pressure that's pushing on the surface of the open bowl. of this. And so we want to fill our barometer with a liquid that does not establish a vapor pressure so that we don't have to worry about pressure inside this tube. Okay, so that's why they used to fill it with mercury. Mercury is ideal for this because it does not escape the liquid form. It does not form vapor pressure up here inside an evacuated tube. Okay, so that's how you make a barometer. Fill a tube, flip it over, let the tube settle down, establish a vacuum at the top, and any extra that comes out of the tube goes into this bowl. So now we have a relationship going on here. We have kind of a push and pull going on here. We have a couple different forces in this image. So I want you to take a minute, take 30 seconds, and see how many different forces you can identify in this picture. Pause the video and do that real fast. Okay, so the forces you should have identified, possibly, would be the force of this column of mercury. Like we said, this column of mercury is really heavy. So if you have a column, if you're holding a column in your hand, you're going to feel that pressure, that force of the column being pulled, the mass of the column being pulled down by gravity over the specific area that the column takes up. Okay, so that's one of the forces. You have this column exerting a force down. The other force we're dealing with here is atmospheric pressure. So you have all of these molecules, air molecules, above this system, above you. And these air molecules are also being pulled down by gravity. And you can think of it as a column, another column, but instead of being a column of mercury, it's a column of air molecules that extends all the way up to the outer reaches of space. And it's pushing down on your hand. Okay, so this is our second force, is air pressure or atmospheric pressure. And atmospheric pressure, all of these little molecules are pushing down on the surface of this bowl. This bowl of mercury is going to be flipped over, or is going to be open to the atmosphere. And so gas molecules can strike anywhere on this surface. And all of those strikes are going to create atmospheric pressure. So we have two forces happening here. When the pressure of the mercury tube is higher, then mercury is going to come out of the tube and go into the bowl. And it's going to cause the level of the mercury to drop inside the tube and the level of the bowl to rise. When we have a stronger atmospheric pressure, the atmospheric pressure is going to push down on the surface of the bowl, and that mercury is going to be pushed into the tube. So when atmospheric pressure is high, it pushes down on the surface of the bowl, and that extra mercury goes into the tube, and the tube level rises. So we have this push and pull in between atmospheric pressure and the pressure of the mercury in the tube. And that is what causes a barometer's level to go up and down. And as the barometer goes up and down, it gives you this measurement of atmospheric pressure compared to the pressure of mercury in the tube. And so this is how a barometer works to function to measure atmospheric pressure. Again, the most common measurements that you're going to see, the most common units you're going to see here are millimeters of mercury. They literally measured the millimeters of mercury in the tube. Sometimes that was called millimeters of mercury. Sometimes that was called torr. Today, we do that little conversion, 760 torrs to 1 atmosphere, and we tend to communicate the pressure in atmospheres. Okay, now the manometer is a slight variation of a barometer. They're very similar, but there's slight variation between them. So let's talk about this. Again, here, look at this drawing right here. And I want you to see if you can identify the forces that are pushing against each other in this drawing. Might be a good time to pause and think about this for about 30 seconds. Okay, and what you're going to see is there's two columns that are pushing against each other. There is a right column from here down to the bottom, pushing down, being pulled down by gravity. And then there's a left column on this side also being pushed down by gravity. Now, the interesting thing about a manometer is one side of the tube is open to atmospheric pressure. So we have the side of the weight of the mercury inside the tube being pulled down, but we have a second force on this side, which is the atmospheric pressure pushing down also. So we can kind of divide the manometer in two, and we can talk about it in terms of like pressure atmosphere plus pressure of our mercury on this side. On the other side, it's not open to the atmospheric pressure. It's open to a bulb. And inside that bulb is where we can get a little chemical reaction to take place. And if that chemical reaction produces gas, then that gas is going to find its way into this tube and it's going to push down. So we have pressure caused by gas that we have produced in a reaction. So I'm going to say pressure of the reaction. You could also, a good label for this would also be like pressure of gas that we created in a reaction. And then again, on this side, you're going to have the tube of mercury pushing down again. So we have this like push and pull that's happening again, only instead of being just the tube of mercury to atmospheric pressure, it's actually atmospheric pressure to pressure of the reaction. Now we can see that in this first example, we have pressure of mercury on this side and pressure of mercury on this side. And if those heights are the same, these two are going to kind of equal each other out. They kind of negate each other. They take each other out of the equation. If you have two forces in opposite directions that are equal, they're going to equal each other out and neither one of them make a difference, right? Okay, so in this first example, the pressure of the atmosphere is equal. The pressure of the atmosphere is going to be equal the pressure of the reaction that we are creating. That is this first scenario. Okay, if we move on to scenario 2, manometer 2, this is not the case. Notice that we have, pressure of our mercury on this side, and it is not equal to pressure on our mercury on the other side. And so we can kind of ignore anything. We can draw a line right here and we can ignore anything under this line because they're going to be equal. But we have to take into account this extra tube of mercury. So we have pressure of our mercury on this side along with pressure of our atmosphere. And that side is going to be equal to the pressure of the gas on this side. So which one is going to be greater? The pressure of the gas pushing out of our reaction or the pressure of the atmosphere? If they were the same, the levels would be the same. Now, in this case, the pressure of the gas is pushing down more than pressure of the atmosphere. And so we can assume that the pressure of the gas is greater. And you can see here, these two, let me erase this up here. These two go together. So the gas in this case is equal to the atmosphere and the mercury combined. Okay, and then we can see finally our scenario 3 is the opposite. We have this column of mercury here plus the reaction, and it is being equalized by the pressure of the atmosphere alone. Again, we're going to kind of draw a line here where the mercury levels are the same and just ignore everything under that line. So in this case, the pressure of the atmosphere is greater. So the gas and the height of the tube together is equal to the atmosphere. The pressure of the atmosphere is greater. Okay, so this is a little bit of like a logic puzzle, a logic game playing with this. We'll go through some examples of the barometer and the manometer in class. You're also going to do some examples in your book, and it's really good to kind of work through this. Draw it. As you read, I highly advise you to draw what you read, and then working out the math behind this at the same time. So try some practice in your book. We'll do some practice together in class, and then we'll move on from there. Okay, have a good day.